Hello everyone. In today's session, we are going to study gradient-based optimization, one of the most important concepts in deep learning. A neural network learns by continuously adjusting its parameters, also called weights, to reduce prediction errors. This learning process is called optimization. In this presentation, we will understand what optimization is, how gradients helps us find the best solution, how gradient descent works, why the learning rate is important, different variants of gradient descent, advanced optimizers like momentum and atom, and finally, how backpropagation computes the gradients required for learning. Before we begin, let us look at today's agenda. First, we will understand why optimization is needed in deep learning. Next, we will learn about gradients, which tells us how the loss changes. Then we will study gradient descent, the core optimization algorithm. After that, we will discuss the learning rate and different batching strategies. Next, we will explore advanced optimizers such as momentum and atom. Finally, we will understand loss landscapes and the role of backpropagation in training neural networks. Why do we need optimization? A deep neural network may contain thousands of even millions of parameters. Finding the best values for these parameters by trial and error is practically impossible. Instead, we use optimization algorithms. The objective of optimization is to minimize the loss function, which measures how far the predicted output is from the actual output. Gradients tells us the direction in which the loss increases or decreases. By following the correct direction repeatedly, the network gradually improves its predictions. As a training progress, we expect the loss value to decrease steadily until the model reaches an optimal solution. Now let us understand the concept of gradient. A gradient is a vector containing the partial derivatives of the loss function with respect to every parameter in the network. Mathematically, it is represented as the gradient of the loss function. The important point to remember is that the gradient points in the direction of the greatest increase in the loss. However, our goal is not to increase the loss, we want to reduce it. Therefore, during training, we move in the opposite direction of the gradient. The gradients are calculated efficiently using the backpropagation algorithm, which applies the chain rule through every layer of the network. Gradient descent is the simplest and most fundamental optimization algorithm. The idea is straightforward. First, we calculate the current loss. Next, backpropagation computes the gradient of the loss. Then we update every parameter by subtracting the gradient multiplied by the learning rate. This update rule is repeated many times. With each iteration, the parameters move closer to the minimum loss and the model becomes more accurate. This repeated process continues until the loss stops improving or reaches an acceptable minimum. The learning rate is one of the most important hyperparameters in deep learning. It controls how large each update step will be. If the learning rate is too small, the model learns very slowly and training takes a long time. If it is too large, the model may overshoot the minimum and fail to convergence. The ideal learning rate allows the model to move steadily toward the minimum without oscillating or diverging. Choosing the correct learning rate is essential for efficient and stable training. There are three common ways to compute gradients. The first is batch gradient descent. Here, the entire dataset is used to calculate one gradient update. It produces accurate gradient, but it is slow for large datasets. The second is a stochastic gradient descent or SGD. Instead of using the whole dataset, it updates the model after processing just one training sample. This is much faster because the updates are noisy. The third and most commonly used method is mini batch gradient descent. Here, small batches of data, usually between 30 to and 256 samples are processed together. Mini batch gradient design provides a good balance between speed, stability, and efficient GPU utilization, making it the standard choice in modern deep learning. Basic gradient descent sometimes moves in a zigzag pattern, especially when the loss surface is a step in one direction and shallow in another. Momentum helps solve this problem. Instead of considering only the current gradient, momentum also remembers previous gradient. This accumulated information helps the optimizer move consistently in the correct direction. As a result, oscillations are reduced, convergence becomes smoother, and training becomes faster. Momentum is especially useful for deep neural networks with the complex optimization landscapes. Several advanced optimization algorithms improve upon standard gradient design. The first is AdaGrad. It adapts the learning rate for each parameter individually, making it useful for sparse datasets. However, its learning rate gradually becomes very small. The second is RMS prop. Instead of continuously reducing the learning rate, RMS prop uses a moving average of squared gradients, allowing learning to continue efficiently. The third and most popular optimizer is ADAM, which stands for Adaptive Moment Estimation. ADAM combines the advantage of momentum and RMS prop. It uses both the history of gradients and adaptive learning rates. Because of its faster convergence and reliable performance, ADAM is one of the most widely used optimization algorithms in deep learning. Training a neural network is like searching for the lowest point in a landscape. Sometimes the optimizer encounters a local minimum, which is lower than nearby points, but not the absolute lowest point. Another challenge is the saddle point, where the surface is flat in one direction and curved in another. Here, gradients become very small, slowing learning. A plateau is another flat region where updates become extremely slow. Finally, a ravine is a step into steep in one direction and shallow in another, causing the optimizer to zigzag instead of moving directly toward the minimum. Modern optimizers such as Momentum and Adam help overcome many of these challenges. Backpropagation is the algorithm that computes gradients efficiently. Training begins with a forward pass where input data moves through each layer until the network produces a prediction. The prediction is then compared with the actual output to calculate the loss. Next comes the backward pass. The loss information flows backward through the network. Using the chain rule of calculus, each layer computes its own gradient. These gradients are then used by the optimization algorithm to update the network parameters. Without backpropagation, gradient design would not know how each parameter affects the final prediction. Let us summarize today's session. The gradient points toward increasing loss, so we move in the opposite direction to minimize the loss. Gradient descent is the basic algorithm used to update network parameters. The learning rate controls the size of each update and greatly affects training performance. Advanced optimizers such as Momentum and Adam improve the speed and stability of learning. Finally, backpropagation efficiently computes gradients using the chain rule, making deep learning possible. Together, these concepts form the foundation of training every modern deep neural network. Thank you.